In this lecture, we will analyze the main and basic characteristics of imperative programming and compare it to the possibilities in functional programming and the possibilities in scheme. We will start with sequential control, and this is about the order of execution of commands. So here we care about first executing C1 and following that C2. So the order of computation is important. C1 and C2 are both commands. So to which degree can we control the order of evaluation in a functional programming language? So this corresponds to execution of a block in a C language, such as, for instance, a block where we increment a variable I and we do something based on the value of I. Here it is, of course, very important that we first do this and after this we do that. In the universe of expressions, the order of evaluation is well known from the comma operator. So this is sequential evaluation of an expression. First E1 and then E2, and the value of the whole thing is the value of E2. So the purpose of E1 is, in most cases, to perform some side effect on variables. Here is an example. The first expression is an assignment expression where I becomes 1, and the next expression is another assignment where j becomes 3 higher than I. This is a typical fragment found in a for loop in C or C++. And it is indeed an expression. Now let us play with the possibility of controlling the order of evaluation in scheme. The question is, do we know in which order these two expressions are evaluated? And the answer is no. C1 may be evaluated first, following that C2, and then there is binding to the parameter. Here we don't know in which order C1 and C2 are evaluated. And that's typical for functional programming. We do not care very much about the order of evaluation. So the question is, can we control it at all? The answer is both yes and no. So if we are working in a programming language like Scheme with eager evaluation, applicative order evaluation, this construct will assure that C1 is evaluated first. It is bound to this parameter. We call it unused, because the real purpose of evaluating C1 is probably some effect. And then we are not really in the business of functional programming anymore. But C1 first, bound to a parameter, and after that we evaluate C2. So this construct is a possible way to control the order of evaluation, at least in an eager or applicative setup. And Scheme is eager and applicative with respect to evaluation order. We will see that in another lecture where we care about evaluation order. It is perhaps a little bit strange that we bind the value of C1 to unused. So why not forget about the evaluation of C1? We don't need it, so why spend time evaluating it when we don't use it? So that may be another strategy for evaluation order, and indeed this is the key to normal order evaluation or laziness. In Scheme there is a begin construct. It is not very useful in functional programming because it is used in situations where Scheme is used for imperative purposes, namely where we want to have the effect of this expression before we evaluate C2. So Scheme, as you know, is not exclusively a functional programming language. It's a multi-paradigm language, and you can do imperative programming in Scheme if you care. Now let us discuss jumps. We all know that jumps are not really recommended in imperative programming, but nevertheless we can analyze jumps to find out what are the possibilities regarding jumps in functional programming. So here we have a tiny piece of a program where we have two labels, L1 and L2. So these are targets for jumps. And here are gotos in the program. Some of them are conditional. So this is a typical little piece of program. It's almost impossible to see what's going on, but these are the conditions when we are using gotos. Here I show a compilable program, a C program, which is a counterpart to the program we have just seen. The upper part here is just establishing names for dummy things. So here we have the program, and this is more or less the same as we saw before. So this is a real program, the C program. I take the liberty to rewrite the program to something which is slightly more complicated. It's basically the same structure with two labels and the same gotos, but I make sure that every if then also have an else. So there's an else here and there's an else here, instead of just continuing after an if where I have a goto. So this is a slight rewrite without changing the meaning of the program. So now I want to show that we can actually come quite close in a functional scheme program to this ugly imperative jump program. The basic observation is that in functional scheme programming, a tail recursive call is a jump with parameters. So a call of a tail recursive function without parameters is then just comparable to a straightforward and plain old-fashioned goto. So with this observation in mind, we take the program here on the left that we have seen, and we program on the right counterpart in Scheme with use of tail recursive functions. So which function do we have? We have L1. So there is one function per label, L1, where we have a goto here, and a goto here, and a goto here. So these calls of L2 and L1 are all tail calls. So we see that it is in fact possible to program a function in Scheme which mimics the control structure that we obtain when we use gotos in an imperative program. This is not recommended, and I will not recommend this style either. But if we really want to do something similar to gotos, what we should have in mind is tail recursive functions with or without parameters. The next item on the agenda is selection. So control structures like if and switch. And here it is relatively straightforward, because as a fundamental mechanism in every functional programming language we have an if. So depending on the value of a Boolean expression, we either evaluate E1 or E2, so, but never both. One of them is evaluated based on the value of C. So this is quite close to selection in if or switch selective control structures. So with respect to selection, we have similar mechanisms in both imperative programming and functional programming. There are no big problems with respect to iteration either. We don't have iterative control structures. We don't have control structures in functional programming because it does not make sense. There is basically nothing that we really want to control the order of. But let's take a look at a sample function, Euclid's algorithm for computing the greatest common divisor. So this is a small C program where we, based on two integers, small and large, compute the largest number which can divide both small and large. Let us see the counterpart to this in Scheme, and the stand-in for iteration, as of here, of this while loop, is of course recursion. So recursion is more than powerful enough to deal with all cases where we need iteration. So here we are lucky enough that we can use the function we have here and the function we have here. We can use the function as such in order to control the iteration. If it is the case that we do not have a function directly at this point where we have the iteration, we must, in a functional programming context, introduce a new function to do the iteration. And that's a very useful situation in the middle of a function where you would, in an old-fashioned imperative way, make a loop. In functional programming, you should introduce a new function which will do the job. What about this function we are working with here? Well, it's not just a recursive function, it is a tail recursive function. This is a tail call because it never returns, it does something extra in the function, so it's a tail call. So it also means that these two variables, which are assigned together with rem in the iterative counterpart, are actually updated when the tail recursive functions call each other. Nevertheless, it's a functional program. There are no assignments, there are no side effects, there are no variables which change value here. In principle, from one call to the next, these variables, these parameters, are new variables which are introduced. In the optimization, which follows tail recursion, we reuse small and large, but that's another story. Now about assignment. There's no doubt that we don't have assignment in functional programming, and assignment is really what we want to get rid of. We want to program in another way in order to avoid all the troubles we have with assignment in imperative programming. Nevertheless, there are certain kinds of assignment, there are certain assignment situations which we can approach in functional programming. So let us see. I took a function from my imperative programming class which solves a quadratic equation with these coefficients: ax squared plus bx plus c equals 0. Find the roots. And here we have 3 local variables which are assigned at the red spots here. And so there are 4 assignments around. Can these be approached in functional programming? Yes, they can. And the reason is that these assignments are only name bindings. So we never really change the value of an existing variable. We only assign a value to a variable in order to have a convenient name for it. So it is name binding. And in fact, I could easily program in a style in C where I, instead of assignment, used initialization in the slipstream of variable declaration. So these simple assignment, these single assignments can easily be dealt with within name bindings in a scheme counterpart. So we see it here at the blue spots. We have name bindings in name binding constructs. Here I just use let, so we bind discriminant, root 1, and root 1 and root 2 here. So whenever it is just about a name binding, where we quite often use assignments in imperative programming, there's no problems. With respect to state, mutable state, let us review this program that we saw a moment ago, where we do a lot of assignments, updating of these variables. So in a while loop, we update 3 variables with the purpose of finding the greatest common divisor in the well-known fashion. We saw the counterpart here in scheme, where we do not use assignment, but we pass existing value of large and small to a new call to our function, where we have new instances of these variables. Now, as we saw before, this is a tail call. In reality, we reuse the locations for small and large, but again, that's another story. So in the situations where we iterate and where we update variables in an iterative process, we can in functional programming program a function with parameters, and we can do state transitioning in these variables through the loop. That's doable. But when it comes to assignment in general, take a C function where you do a lot of assignments independent of iteration, so on and so forth. Well, of course, that cannot be done, and it should not be attempted in functional programming, because it causes a bunch of problems that we want to avoid. So this is a situation where we will switch to another mindset and do our programming in another way. Let us finally discuss objects and object mutation. So that's a natural continuation of both assignment and state transitioning. So here we have a simple situation where we have a point implemented as a simple struct, and we have a move function which takes a pointer to a point as first parameter, and dx and dy as second and third parameter, and we mutate the x and y by assignment. In main, we create a point, and we move the point. So we have been able to mutate the state of an object through a reference or a pointer. This is, of course, also a situation we want to avoid in functional programming. And what is the typical way to deal with it in functional programming? What is the workaround? Well, we can make a point. Here I make it with list programming, so I make a tagged list, tag it with a simple point. Other possibilities exist. It's not really crucial that we use list. We could use some available stock mechanism if that was the case. We can make selector functions here with compositions of car and cater. I make a new point p, and the crucial point here is that I program a move function that returns a moved copy. So instead of mutating the state of the object, which by the way here is accessed via a reference or a pointer, because lists are really reference types in Scheme, instead of mutating the x and y fields or positions in my list, I avoid that. If I want to move the point, I create a new point, which I return, and the new point is repositioned relative to the existing point. So the repositioning takes place here. So this is two counterparts, one where we have mutable objects and one where we have non-mutable objects. And if we need to change something in an object, we create an updated copy. So the original will still be around. The change that we want to make in our world is governed through a new copy of the object. The old copy may be important in the future. If it's not, it will disappear through garbage collection.